prácticamente no hace falta que presente a nuestro próximo conferenciante. Se trata del profesor Carlos Frenk, de la Universidad de Durham. Para los que no trabajáis en el tema, Carlos fue uno de los padres de los modelos de materia oscura que se desarrollaron en los años 80. En los últimos 30 años ha sido un punto de referencia en las simulaciones cosmológicas, investigador principal del Virgo Consortium. Supongo que habréis visto esas maravillosas simulaciones del Millennium, y actualmente es el director del Institute for Computational Cosmology de la Universidad de Durham. Quiero agradecer a Carlos su presencia en la reunión científica de la SEA y, bueno, quiero avisar que además de esta conferencia invitada en la sesión inaugural, Carlos impartirá una conferencia pública el próximo viernes a las 7 de la tarde en la Facultad de Medicina, a la que estáis todos invitados. Después de esa conferencia pública, además, tendremos un acto lúdico con música y astronomía.
Sí.
Esperemos que no se me acabe. Si me acaba la electricidad, tomaremos alguna. No te preocupes, está bien. Está bien. Okay. Muchas gracias, Javier, por la introducción. Es un gran honor estar aquí. Mi idioma materno es un dialecto del castellano del siglo XVI, que se llama el español. Pero voy a seguir la recomendación del profesor Bonanno y en vez de dar una conferencia en mal castellano, lo voy a dar en mal inglés, por lo menos con acento español. Okay, so I hope you can understand, if not my English, at least my accent. So, I'm going to talk about cosmology, and in fact, it turns out that it's now almost exactly 30 years since Alan Guth put forward an idea that was to change our view of the universe. And this is the idea that very soon after the Big Bang, 10 to the minus 35 seconds after the Big Bang, the universe underwent a period known as inflation, where it expanded very rapidly for a short period of time. The inflation was triggered by tapping the vacuum energy of some quantum field that was assumed to be present at early times. Now, this idea was revolutionary for many reasons, particularly because since quantum fields are evolved and quantum fields are always subject to quantum fluctuations, the universe was seeded by small fluctuations that, according to the ideas put forward then, could have developed into the galaxies and other structures that we see in the universe today. So this was a very profound, revolutionary notion, the idea that we could trace back galaxies and cosmic structure to quantum fluctuations of the vacuum at these very early times. Around the same time, 1980 or thereabouts, the idea was put forward as well that perhaps the dark matter, which I should say around then wasn't accepted by everybody, the idea that dark matter could consist of some form of elementary particle produced very early on after the Big Bang. And it soon became apparent that a very good candidate for the dark matter would be a supersymmetric particle that would have been produced very early on if the universe underwent a period where supersymmetry, that is, a symmetry between hadrons and electrons and so on, if that supersymmetry existed at early times. And the result of supersymmetry is the production of particles that are very quickly interacting and could, in principle, provide the dark matter. These ideas then were developed throughout the 1980s and became enshrined as what we now regard as the standard model of cosmogony, also known as lambda CDM. I'll tell you about lambda in a minute. CDM stands for cold dark matter, which is precisely what these supersymmetric particles would be. What I'm going to talk about today is I'm going to describe what this cold dark matter model is, and I will tell you about what next. If you look in your program, I'm also going to talk about the satellites of the Milky Way, because you will see then that, in fact, they probably hold the clue to our future progress in cosmology. It's part of the progress in this subject. So let me then start from the very beginning and tell you what a cosmological model is. It's a model that seeks to explain the dynamical evolution of the universe and the formation of cosmic structure. If you want to do a cosmological model, you have to specify 4 ingredients. You need to know what the universe is made of. You need to know the initial conditions, the way in which these initial conditions are amplified, and of course, like every theory in physics, you need parameters, in this case known as the fundamental cosmological parameters. We now know that the contents of our universe, and this is something that's derived largely empirically, has this very bizarre composition in which only about 4% of the content of the universe is normal matter, normal atoms. 21% is dark matter, which in this standard cosmological model would be cold dark matter, a supersymmetric particle perhaps. And then the lion's share of the content of the universe is dark energy. This is a result largely empirically derived, and what is quite surprising and amazing is that when you add up all the 3 components, then the total comes very close to the critical density required for the universe to have the simplest geometry, which is a flat geometry. So it's one of the great successes of cosmology in the last decade. Now, from the point of view of the formation of structure, what we care about primarily is the dark matter, because that's what produces the agent that shapes our universe. Now, the dark matter can, in fact, as recognized in the 1980s, it doesn't need to be cold. It could also be either hot or warm, and that depends, really, this nomenclature stems from the fact that what really matters from the point of view of the formation of structure is how these particles move at early times, just relative to the temperature of the universe. So cold dark matter are just very cold particles. For the most part, they're cold because they're very massive. Neutralino is a generic word for a supersymmetric particle, and they are very massive particles with a mass of in excess of 100 GeV. There could be also axions, which are very light, but they have the same effect as these very massive particles because they're never really in thermal equilibrium. But the dark matter could have been hot or warm, and in the 1980s, hot dark matter was very popular because there was a report from the Soviet Union that Lyubimov had measured a neutrino mass of about 10 or so electron volts, which would have meant that the dark matter would have been of this hot variety, hot because these particles are very light. Warm dark matter, there were no candidates in the 1980s, but in recent years, some candidates have been put forward for this possibility. Now, the initial conditions, as I just indicated, the second of the 4 elements is provided in principle by inflation. And inflation actually predicts a very simple power spectrum for these initial fluctuations, these quantum fluctuations. The power spectrum is simply proportional to the first power of the spatial frequency, and the amplitudes of these fluctuations have a Gaussian distribution because these are quantum processes that are uncorrelated, and they produce a Gaussian distribution of amplitudes. According to the standard model, these small fluctuations are amplified by gravitational instability. Fluctuations grow, reach a maximum size, and then recollapse. And fluctuations that are denser collapse earlier than fluctuations that are less dense. So galaxies would collapse first, then clusters, then superclusters. And as I said, there are parameters that describe either the contents of the universe or the properties of these primordial fluctuations, as well as the rate at which the universe expands. Now, when you look at this set of ingredients, and I have looked at them for many years, you have to admit that lambda CDM is really a pretty crazy idea. I mean, who would dream of thinking that galaxies come from quantum fluctuations. Seems, frankly, completely insane. And it is quite insane. It is what I call an a priori implausible model. The reason, however, why it's so popular is because it makes very definite predictions that can be tested against observations. And that's why this subject has advanced so rapidly, because it makes this model makes very definite predictions, and these are encapsulated in the power spectrum of fluctuations that emerge after the Big Bang. So what's plotted here is the amplitude of fluctuations, or the power spectrum, as a function of scale, a wave vector k. These are large scales, these are small scales. Inflation produces a power law, but this power law is modified during the Big Bang phase by damping processes that depend on the nature of the dark matter. So for example, if the dark matter is, I've indicated here some astronomical objects just to orient you on this map. So if the dark matter is a 100 GeV supersymmetric particle, then the power spectrum has this characteristic shape with a cutoff, and the cutoff is at a very small scale, corresponds to 10 to the minus 6 solar mass, is an Earth mass. So that's because these particles are so heavy that free streaming, which is what produces this cutoff, is on very small scales. But if the dark matter was something else, then in principle this cutoff could occur on larger scales. The cutoff due to free streaming of these particles in scales inversely with the mass of the particles. So for example, if the dark matter was not cold, but if it was a warm dark matter particle, then because the mass is smaller, the cutoff occurs at larger scales. For example, for a particle with a mass of a few keV, it would occur on the scale of dwarf galaxies. So you can see here how, in principle, by looking at dwarf galaxies, one can tell, in principle, whether the dark matter is cold or warm. And I will come back to that topic later. I should just say that there are limits on the mass of the dark matter particle because of this cutoff, coming, in fact, from studies of the Lyman alpha forest at high redshift. We constrained the mass to be in excess of a few keV, but we don't really know whether the mass really is 5 or 10 keV, or whether it is 100 GeV without further work. Now, so the cold dark matter cosmogony, in fact, goes back to the 1980s. This was the first paper that worked out that power spectrum that I just showed, and also made predictions for what we would expect to see reflected in the temperature of the microwave background. This was the first paper that worked out how the universe would evolve, how structure would form from these initial conditions. And this paper laid out in a very elegant way a large part of the mathematical framework, particularly the statistical framework that underlies our understanding of how structure grows from these quantum fluctuations. Now, so it was very clear already 25 years ago that a cold dark matter universe, this is what we now call lambda CDM, it's a simulation from those initial conditions. Cold dark matter universe looked a lot more, looked a lot closer to the real universe as was known then. This was the largest redshift survey of the 1980s, the CFA redshift survey. It was clear that lambda CDM looked a lot more like the real universe than, say, a universe with Lubimov's neutrino mass of about 30 electron volts. Here, because the mass is so light, the cutoff in the power spectrum is very large, and that is reflected in the emergence of these very large structures that are not seen in the real universe. So this was one of the first examples of how cosmology can give input into particle physics. It was clear that Lubimov's experiment couldn't be right. The neutrino couldn't have a mass as large as a few tens of electron volts, because it would create completely the wrong universe. And we now know that the neutrino mass is much smaller by many orders of magnitude than about 30 electron volts. But it was clear already then that CDM was a good bet. And I should say the 1980s were wonderful, largely because there was hardly any data, and it was a really good time to be a theorist. This biggest survey, which had taken many years to compile, had a grand total of 2,873 galaxies. I remember almost each of them. And that was pretty much all the data we had. So theorists had free reign, and that really was a golden era for cosmological theory. I remember giving talks where skeptical audiences would throw tomatoes at me because they thought this was all pretty crazy. which I should say I agree with them. It was, and it is, a pretty crazy thing. But what really enshrined this as the standard model was the measurement, the discovery in 1992 of fluctuations in the temperature of the microwave background radiation, and these fluctuations, which were then remeasured a decade later by WMAP, these gave the absolutely surprising result that maybe these ideas were not as crazy as they seemed at first sight. So this is this very iconic plot that I'm sure you've all seen before. Most physicists have seen it before, and really it's a tribute to our science and to the way in which our subject has advanced. So what's plotted here is the power spectrum of fluctuations in the microwave background temperature, again as a function of angular scale on the sky. The theoretical predictions are shown here in blue. They're non-trivial. These oscillations reflect coupled oscillations of the photon baryon fluid during the Big Bang phase prior to recombination. The universe is oscillating, and you see that oscillatory pattern in the power spectrum of these fluctuations. The blue line then are the theoretical predictions that go back to Jim Peebles in 1982, and the data points are the data from WMAP. And I think this is a plot that really deserves our greatest admiration, really a true breakthrough in our understanding of the universe. However, the microwave background only probes conditions very early on, when the universe was 1,000 times smaller than it is today, and these fluctuations were very small, 1 part in 100,000, and there's still a long way to go between that and galaxies like this one, which have over densities 11 orders of magnitude or more larger than these temperature fluctuations that we see in the microwave background radiation. So how do we go from here to there? Well, we need to do physics, and actually, in fact, the primary agent that drives structure, according to the standard model, is gravitational instability. So we need to understand gravity, which fortunately is a relatively simple force. If we, however, also like to understand the visible part, what this 4% of baryon does, then the problem is much more complicated because we need to understand gas dynamic and radiative physics. Here, these processes are best and probably only calculated through simulations. And that's why the subject of simulations is central to an understanding of the evolution of structure in the universe. So let me show you a movie that illustrates just dark matter, how dark matter becomes structured as a result of gravitational instability. So these, you see these at a very early time, 60 million years after the Big Bang, a sphere of size, whatever that is in megaparsecs, 150 megaparsecs across. This has these quantum fluctuations, this power spectrum that comes from inflation imprinted upon it. It's only dark matter, so only gravity plays a role. And you see how very quickly the universe goes from being very smooth to being quite complex. Material flows into these lumps, which are arranged in this sort of characteristic filamentary appearance that emerges from these quantum fluctuations. And the universe very rapidly goes from being very smooth to being very highly structured in characteristic patterns that you see very nicely developing in these simulations. So now let me show you a fly-through, a dark matter universe. This comes from something called the Millennium simulation. And it is it's where my computer says, this is a crazy idea. Let me try again. It's done that before, so what I can remember is how to get it back. Oh, I think I need to go somewhere else. Here, for example. Let's see. Right, that looks good. Okay, so here we are flying through this universe of dark matter at the present day. This is from something called the Millennium simulation. And you see this huge richness of structure that emerges from these quantum fluctuations. There's lots of dark matter halos, which are these little lumps. And of course, there are many more small halos than big halos because the power spectrum increases towards small scales. It's all dark matter. You see these filaments here that form at their intersection these very large lumps, which this one, for example, would correspond to the mass of a galaxy cluster. A galaxy like the Milky Way would probably form in a halo like this when gas cools and collapses and turns into stars eventually. So this is what a dark matter universe would look like, with this huge richness of structure and this very intricate tapestry of filaments surrounding lower density regions known as voids, which you see here very nicely. So this is what emerges from this very simple inflationary quantum fluctuations. Quite amazing that that very simple power law eventually develops into this very rich structure. So we understand what the dark matter does, but of course we only see the visible matter. Here is a map of the galaxy distribution from the 2-degree field galaxy redshift survey, where we surveyed 2 patches of sky in the north and in the south. And how do we compare these observations with the theory? Well, the theory is simple, in simplest form, tells us about the dark matter. We need to figure out how this dark matter universe is populated by galaxies. And the way we do that is well, it's quite complicated. There's a whole community, of course. Many people represent that community in this audience. How do we go from a dark matter universe, and in particular, from the distribution in mass of halos? This is just the halo mass function, how many halos per unit volume. It's a function of mass. How do we go from there to the visible universe, where we can count, for example, galaxies as a function of their luminosity? This is the luminosity function from the 2-degree field galaxy redshift survey. So to going from this dark matter universe to the visible universe, we need a theory of galaxy formation, of course, and that is another subject where there has been enormous progress in the last few years. There are various ways to try and implement the theory of galaxy formation. One would be to try and do a simulation, including all the baryonic physics that we know are relevant. That would not be possible in a simulation this size, because these gas dynamical simulations are complex and very computing intensive. There's an alternative where one looks at the history of formation of one of each of these halos, and then tries to model semi-analytically all the key physics that we know are relevant: gas cooling, fragmentation into stars, and very importantly, feedback effects. And that is known as semi-analytic modeling. And here are the results of applying these sort of ideas to the Millennium simulation. This is the universe as seen in light. This is the universe as seen in dark matter. And you can see that, roughly speaking, not surprisingly, the galaxies trace this cosmic web, because, of course, they form in the halos that trace out the cosmic web in the first place. So this is what the universe of dark matter looks like. This is what the universe of galaxies looks like according to the semi-analytic models. Now, we can then proceed to try and compare all these ideas with observations. Here's the plot where on the right-hand side, this is the virtual universe, this is the Millennium simulation, and where here we've taken a slice trying to emulate the selection effects and the geometry of the 2DF. And you can see by eye that there is quite a good correspondence. This is longitudinal sky survey with a great wall. Here is the counterpart in the Millennium simulation. And this is the old CFA redshift survey from the 1980s. Here is what it looks like, or a region that we deliberately tried to make. We found one that looked roughly like this famous stickman from the 1980s. But we can do these comparisons in a quantitative way by, for example, plotting the power spectrum of the 2DF galaxy redshift survey, so shown here by the symbols with arrow bars. And here is what the theory predicts. Again, an amazingly good match between the theory and observations. And if you look closely, you see that both theory and observations have something weird here, some kind of feature there. Let me amplify that for you. That's the same data as before, but not amplified. And you can see that the theory predicts some oscillations here, which seem to be replicated in the data. And those oscillations are actually known as the baryon acoustic oscillations, and they're exactly the same phenomenon as what we saw in the microwave background radiation. These coherent oscillations of the photon baryon fluid way back in the Big Bang left an imprint in the dark matter distribution, which is inherited by the galaxies. And here it is in full glory, shown in the 2-degree field galaxy redshift survey. And this is, demonstrates very nicely that structure almost certainly grew by gravitational instability from those initial conditions. And I should add that the same was found just a few months after I talked about this in Stanford in the US in 2004 by this longitudinal sky survey. They used a different survey, of course, the Sloan survey, and a different analysis method. They looked at the Fourier transform of the power spectrum, the correlation function, where those oscillations show up as a bump. And so these baryon acoustic oscillations have now become an industry because the position of this bump, or the wavelength of the oscillation, depends on the geometry of the universe. And so because we know it comes from the Big Bang, and we know this feature is related, in fact, to the acoustic horizon at recombination, if we can measure this feature at different redshifts, we can trace the geometry of the universe and therefore set constraints on the dark energy. So here is a summary of where cosmology stood 5 years ago or so, where we have the power spectrum, again, as a function of wave number. Here, the WMAP measurements have been extrapolated to redshift 0 using linear theory, and here's the 2DF measurements. And you see that over a range of a factor of well over 100 in scale, from essentially several gigaparsecs, the horizon size, to about 10 megaparsecs, the CDM model gives a wonderful description of what we see both at redshift 1000 and at redshift 0 over a scale from 1000 to about 10 megaparsecs. So that, I think, is an undeniable success of the theory, but you have to pay a big price for this success because this comes at the expense of assuming a dark energy component, some mysterious stuff with negative pressure, at the expense of assuming that structure was seeded by quantum fluctuations during inflation, and that the dark matter is some yet to be discovered elementary particle, possibly a supersymmetric particle, and we don't even know that supersymmetry, in fact, ever happened. So it's a high price to pay, and an important question is, what are the prospects for testing these three fundamental assumptions of the theory? Well, the dark energy, I think, is a big, big problem. Many people feel that maybe it's to do to Einstein, is to connect it with Einstein's cosmological constant. The problem with that is that current physics, essentially GR, and quantum physics predicts a natural value for the cosmological constant, the Planck value, which is a mere 10 to 122 times larger than the value observed. And I think everybody will agree that this must rank as the most inaccurate prediction of fundamental physics ever. You really have to work hard to get it this wrong. So what this tells us is that the cosmological constant is not something that fits in with our current understanding of physics. It requires new physics. And what it is, I don't think anybody knows. And I think this is as good a bet as anything else. We really don't know what it is. Now, if it could be that general relativity needs to be modified or extended, and many people, including some here, work on that idea. In the context of standard general relativity, this is usually expressed, this component of dark energy is expressed through an equation of state relating the pressure to the density, and there's this equation of state parameter, which is exactly -1 for a cosmological constant. Now, the interesting or exciting part of this discourse is that, in principle, W could be constrained experimentally by these baryon acoustic oscillations I just mentioned, by type 1a supernovae, which are standard candles, or by measuring the growth rate of structure, which is sensitive to the dark energy. And there are many experiments in Europe and in the US trying to pursue this kind of program. The current constraints on W are summarized here from these sort of tests that I just mentioned, baryon acoustic oscillations, supernovae, and so on. And W seems to be very close to the value required for a cosmological constant, to about 5% or so. But I always think that if we measure W to be -1, we're great, but we're none the wiser, because we might have a name for the thing. It's called the cosmological constant, but what is it? We still don't know. So this is one of the frontiers of the subject. Now, what about the idea that galaxies were seeded by quantum fluctuations from inflation? How do we test that? Well, it is very exciting because it turns out that it is possible to test this part of the standard model, because during inflation, these quantum fluctuations cause the universe to vibrate. And the result of that vibration was the generation of gravitational waves. Now, these gravitational waves from inflation, amazingly, are in principle detectable through so-called B-mode polarization of the spectrum of the microwave background fluctuations. And in fact, in principle, the Planck satellite could actually, in principle, discover this B-mode polarization, which really would be the smoking gun of inflation. But we'll have to be very lucky because it turns out that the amplitude of this B-mode polarization is many orders of magnitude below the already very small temperature fluctuations in the microwave background radiation that you see here. So it's a forecast for, in an optimistic case, the amplitude of this B-mode polarization, which you see is 5 orders of magnitude below that already very small signal, but perhaps Planck will find it. So now, the area of the model where I think we will see lots of progress forthcoming in the next few years is the third one, where I think there's everything to play for. So I'll make a forecast, namely the dark matter will be discovered probably within the next 2 or 3 assemblies of the Sociedad Española de Astronomía. Now, I have to warn you, I made this forecast already before, and so far I've been wrong, but I think it is quite possible that the dark matter will soon be found. In the meantime, we can try and look for its signature in the Milky Way. And let me tell you how we do that. It turns out that the Milky Way provides 3 very nice ways to try and establish the nature of the dark matter. I've listed them here. I'm going to run through these quite quickly. So firstly, the structure of dark matter halos. In cold dark matter theory, there is a very well-defined prediction for what dark matter halos should look like. Here's a movie of the formation of a galactic halo. Here's the clock, 70 billion years after the Big Bang. Here's the scale. And you see here at very early times, of course, the universe is very smooth. These fluctuations are very small. But here, at redshift about 30 or so, you begin to see the formation of the first 100 solar mass objects, where by this time, the first stars would begin to form. And already at these very early times, there's this sort of incipient cosmic web that arises, but here are the places where the first stars that would reionize the universe would form. By this time, redshift 10 or so, there's many such sites of the first star formation reionizing, probably producing UV photons that reionize the universe. And you can see here this beautiful merger of several lumps occurring along a filament, building larger and larger structures. That's why we refer to these processes as hierarchical clustering. This object here at redshift 6 is already nearly 10 to the 12 solar masses and still living a very dangerous life. Here's an object. Just look at this one. It's going to go through the center, and when it goes through the center, it gets a spray of particles that are tightly stripped. It seems to like it, so it comes back for more, and every time it goes through it, it becomes smaller and smaller and smaller because it's being tightly stripped until just a little nugget is left at the end. Here, at this point, this object now has the mass of a Milky Way halo, and you can see that all this activity is beginning to die away and creating the conditions necessary for gas that's spinning because it has angular momentum to cool and form a disk like the disk of the Milky Way. So from now on, this object pretty much stays as it is, and presumably that is when the disk of a galaxy would form, and the movie gets a bit boring, so let me move on and tell you that in spite of this complexity in the formation of these objects, it turns out that the density structure is very simple, and that is something that Julio Navarro, Simon White, and I found over a decade ago, 15 years ago almost, that no matter what the mass of the object is, from dwarf galaxies to galaxy clusters, the density profiles are described by this very simple formula, which has a very important property that towards the center, it's divergent. So the density profile diverges like 1 over r towards the center. In other words, the theory predicts that the centers of halos should be really dense, really cuspy. And that, if we could disprove this, if we could show that nature doesn't have these cuspy profiles, we could then disprove the whole theory. I should say that these simulations were very simple. We only were able to afford 10,000 particles. We can do much better now with simulations with 1.5 billion particles. These are images of 6 halos that we've done as part of the Aquarius program of the Virgo Consortium. That's a large international collaboration. Here are some of the people who've been involved in this program. This is my favorite list of collaborators. because when you arrange them in alphabetical order, I come top. So I really like these guys. And we've been doing simulations of galactic halos for a while. And one of the first surprises was that whereas the work from the 1970s was only able in a galaxy to resolve the density profile in the other parts of the Milky Way, it turns out that with these new simulations, we can extend this all the way to just a few tens of parsecs, and our old formula works really well, which maybe is just good luck. This NFW profile, these Cosby profiles give a good match to the simulations, not perfect. There are discrepancies of 10 or 20%, but for the most part, this is a good match to the simulations. And the main thing is that they produce this Cosby density profile. So question is that there's no doubt that the theory makes this fundamental prediction, the Cosby density profiles. In principle, you think, well, astronomers should be able to test that. And in fact, of course, astronomers try to test that and ask the question, does nature do what the simulation does? Where would you go looking? Well, you would go looking in galaxies and clusters, see if they have Cosby halos. But that's not easy because galaxies and clusters, of course, have lots of baryons in the center. And these baryons could modify the galaxy, the halo could be modified by the galaxy forming in it. So a lot of people work on this, but it is a complicated subject. However, this is one of those examples where nature has been kind to us by giving us objects, namely the satellites, the dwarf satellites of the Milky Way, where the baryons are so few and so unrepresented that we have a genuine hope that we can actually see directly the dark matter profile. And moreover, these dwarf satellites are quite nearby, so they can be studied in some detail. These dwarfs have mass to light ratios of 1,000, indicating that the halo is pretty much untouched by baryonic effects. In the last few years, and the theory, by the way, predicts also Cosby profiles for these subhalos. So we know there are satellites in the Milky Way. There's about 30 or so discovered so far, but for 6 of those, shown here, in the last few years, this has been possible to measure with great accuracy radial velocities, in the case of Fornax, for example, for about 3,000 stars, less in the others, but still several hundred. So these 6 galaxies, Fornax, Sculptor, Leo 1, Sagittarius, Carina, and Sextans, these innocent-looking satellites of the Milky Way, could in principle bring down the whole edifice of cosmology if we were able to show that they don't have Cosby profiles. So the question I'm going to ask and try to answer in the next 2 minutes is whether these Cosby profiles predicted by the simulations, are they consistent with the photometric and kinematic data for these 6 dwarfs? So the first attempt at answering this question would direct you to look at the Jeans equation shown here that relates the potential, what we want to know, to essentially the pressure. This is the, combine these two terms, this is the density, stellar density profile. This is the velocity dispersion. Rho sigma squared is the pressure, that's a pressure gradient. And this in principle measurable from photometry. This in principle can be estimated from the spectroscopy. But unlike a gas where the pressure is uniform, in a stellar system, you can have different pressures in different directions because it's a collisionless system, and that is indicated by this velocity anisotropy term. So I'm going to take the simple case where this is 0, and then these 2 quantities can be measured. And so what we're going to do is this work with Louis Trigari and Simon White, that's on AstroPH, go to each of these halos, assume, for example, that Fornax formed there. We know the potential Gm over R. Assume Fornax formed there. We can then predict the radial velocity dispersion profile, compared with observation, obtain the value of chi squared, go on to this fellow, assume Fornax forming there, do the same operation until we find the best fit halo to Fornax, and then we do this for the other 6 halos. Here are the results. So the lines here are the predictions from the simulations for the radial velocity dispersion profile for the 6 satellites. And you can see that the model predictions agree perfectly well with the data, indicating that as far as we can tell, the data are consistent with Cosby profiles. I haven't proved the Cosby profiles are there. However, all I proved is that the data are consistent with that. And you can do more fancy stuff. if you want to, using the fold velocity distribution function. I've been speaking rather slowly, contrary to what might seem, so I'm going to skip this, but anybody who's interested can just look it up in the paper with Strigari and Simon White. So the main result is that, as far as we can tell, the photometric and kinematic data for the Milky Way satellites are consistent with these COSP-NFW profiles. I say I haven't proved they exist, but failed to disprove that they exist. So and this is a strong conclusion because the Milky Way satellites are essentially dark matter dominated. Okay, now, so that's one part of the problem. There's another problem that people here who work in the subject will be familiar with, known as the satellite problem for cold dark matter. And that is the following. When you look at the simulations, you see many, many subhalos. In fact, there are hundreds of thousands in the Aquarius simulations, and yet, when we look in the sky, we only see a handful of satellites. And so the question is, why so few? What happened to all these other subhalos? Why only 30 satellites when you could have had 300,000? Just imagine how good that would be for the galactic astronomy community. They could get all the telescope time in the world. As it is, they've only got 30 of them to look at. So what is this? Does this signal a big problem for CDM? For example, some people have argued that maybe that tells us that the dark matter has to be warm, because in that case the power spectrum is cut off at a scale relevant to these satellites, and naturally there are no fluctuations on small scales. So here, with a warm dark matter candidate, you do end up just with a handful of lumps. So maybe this is the explanation. Well, I'm going to argue, in fact, that that is not necessarily the explanation, because the key question is, okay, there are lots of lumps, how many of them actually manage to make a galaxy? Now, you might think that making galaxies is easy, but it's really hard, particularly in small halos. And we have the same problem in the field. If you look at the halo mass function, it's very steep compared at the small mass end compared to the faint end of the galaxy luminosity function. And that is because it's really, really hard to make galaxies in small halos for two reasons. One is that stars explode as supernovae, they're very energetic, and they blow out winds from galaxies. They do it even in these big galaxies like M82. They do it even more in small galaxies like the satellites. So it's very difficult for that reason alone to make a big galaxy in a small halo, because the first supernovae just clean it out of gas. And to add insult to injury, also at the early universe, when the universe is reionized, the gas is heated anyway, so it cannot cool in these small halos. And the theory of galaxy formation tells us that we can go from the halo mass function to the galaxy luminosity function by including all this complicated physics, which you can see it's complicated because it has the word feedback. And so the supernova feedback and reionization make it very hard to make galaxies in small halos. And those ideas were actually developed in 2002 in his thesis by Andrew Benson, who implemented them in the context of the Milky Way. Here is the luminosity function of the satellites of the Milky Way, as was known in 2002. There were only 11 satellites known then with this luminosity function. The halo mass function has this very steep shape, but as I say, once you start adding, for example, supernova feedback through a model of galaxy formation, then most of these halos never make a galaxy, and then supernova feedback does most of the damage, and then reionization completes the damage. And so these models then had a luminosity function that more or less agreed with the data, but you can see they made a prediction, which at the time in 2002 was deemed to be a big problem for the model. These ideas predicted that there should be a population of very faint satellites in the Milky Way, which in those days was not known. This is 2002. That was the list of satellites known in 2002. And as some of you will know, from 2003 onwards, a whole host of new satellites were discovered by the Sloan Digital Sky Survey. And the new satellites lie just like where Andrew Benson's work had predicted they should be. Now, so when I show this plot, obviously I feel very pleased with myself because he was my student. But frankly, I think we just got lucky. I think these models are quite complex, and it just turned out that our predictions agreed with the data. but I think one has to moderate that with the fact that these are quite complicated astrophysics. But the main message is that it is not inconsistent to have only a handful of satellites in these Aquarius dark matter halos. Many people have looked at this again. Interesting sociological problem, because they've all solved the same problem again, doing the same kind of ideas. But in any case, here is a current version of the luminosity function of satellites, shown in black, and what the theory predicts. Okay, now, I'm going to skip this, just say that you could do the same problem also using simulations, cosmological simulations, and these, as I say, are very time-consuming and are only suitable for studying the brightest of the satellites, but the results are the same. The luminosity functions of the simulations, now with full gas physics, agree quite well with the data, and I refer you to this paper if you want to see the details. Let me move on to just conclude this part of my talk. As I said, very few of these halos successfully make a galaxy because early reionization and supernova feedback are just not helpful for making galaxies. I briefly want to anticipate what I think will be a very important development in the next few years. If CDM is right, these halos have to be there. They just didn't make a galaxy, but in principle, they should be observable. And they can be observed through lensing, and in particular, through a particular form of lensing, which is sometimes referred to as milli-lensing. And I'm just going to mention this briefly, but essentially, if you have a quasar right really well aligned behind one of these halos, so if the quasar is strategically placed, then it turns out that on the image plane, one gets this so-called critical curve with a few images that are very close to the critical curve. Now, the critical curve corresponds to these caustics in the source plane, and these images near these edges of the caustic produce these very characteristic patterns, which are very well understood. And in particular, these sources obey, near the critical lines, obey a very well-known relationship between the magnifications of these three images, which is known as the caustic relation. So all I need to say, if you're not experts in lensing, is that if the lensing is smooth, then there is a relationship well understood between the fluxes of all these images near the critical source, the critical curve. But if there is substructure, then the critical curve becomes lumpy, and this relationship is violated. And so in principle, all you need to do is find the quasar, measure the amplifications of these images, take ratios of them, and if they don't fall in the formula given here, then you know this object must have substructure. And in fact, these violations have been discovered in 3 quasars. At the moment, the results are very confusing because if you interpret them at face value, they indicate that there's even more substructure than in CDM predicts. So, but it's only 3 cases, and but this, I think, is a subject with great future. And I should say this word by Dandan, I got her name wrong. I forgot, and I'm an author of this, so I should know who my collaborator is. But anyway, it is on AstroPH as well. Now, so I'll just want now to briefly mention a third possible test of where I think there's still a lot of future as well, and that is to do with the fact that, as you saw in that movie, the Milky Way formed from CDM initial conditions. Then all these tidal stripping of halos and presumably stars must have taken place. And indeed, the theory or the simulations, when you put stars in them by some tricks that you can look at here in the thesis of another of my students, Andrew Cooper, then you see that the stellar halo, this is now the stellar halo from these Aquarius simulations, should have lots of structure. There should be lots of streams and lumps being disrupted, and this is all because of this part and parcel of hierarchical clustering from cold dark matter initial conditions. Now, in the last few years, this is what the 6 Aquarius halos look like in stars. They all look very lumpy, very irregular, full of stuff. And many of you will know, in the last few years, Sloan has, in fact, revealed the presence of such streams in the halo of our own Milky Way. Here's a very famous Sagittarius stream. You can see it better here. There are two arms, a trailing arm and a leading arm, and these clearly have all the signatures of tidal disruption. Until recently, observational astronomers always thought of the Milky Way as having sat there doing not much for 10 billion years. Now we're beginning to get evidence that perhaps there's activity going on. There's this spectacular survey called the Panda survey with Spanish participation of the Milky of M31. It's a very deep and extensive photometric survey of M31. And look at all these structures that are beginning to be revealed. Shells, streams, elongated features, substructure, of course, M33 here. And compare that with Andrew Cooper's simulations. And you see here similar kind of structures. There's a shell here. There's something that looks a lot like that. Clearly something being tidally stripped. Here's M33, except it's in the wrong side, but ignore that. And you see this general kind of disorganized situation with the stars seems to be present in the Milky Way. There's some beautiful images taken by a Spanish astronomer using probably some of the smallest telescopes in the world, Martinez Delgado. I don't know if he's here, I haven't seen him, but here are images of a number of galaxies. And again, you see the same kind of story, lots of shells, streams, and so on. And I asked Andrew to compare his simulations with the data. Now here's one that I thought he was joking when he showed this one. This is a simulation, which he says, look at that one. You see that? There it is. See, that's even got a cross there. Look at that. There's a cross. But here's my favorite one. That's a simulation, and that's the real thing. I have to say we cheated. These images in the simulation are deeper than the real ones, but you get the idea that there does seem to be structure of this sort in the halos of galaxies. And perhaps this is giving us evidence for the fact that maybe the Milky Way itself formed in this hierarchical way predicted by the theory. To finish off, I think you shouldn't believe anything that people like myself say about cold dark matter models until and if the dark matter is actually discovered. I think that clearly, we can make any number of beautiful pictures with streams and satellites. I can tell you any kind of stories you like about how hard it is to make galaxies and so on. The ultimate proof would be to detect the dark matter. In fact, the prospects, as I said at the beginning, are very good because there are at least 3 techniques which have now reached maturity. First of all, of course, we might find evidence for supersymmetry in the LHC. And the experts tell me that if LHC exists at the right energies, TeV or so, the LHC should find it within a year or so. So keep tuned for that. There's a lot of activity going on trying to detect dark matter in underground laboratories, and I think there's some talks about that this afternoon. But another very exciting possibility is that the dark matter might be detected because it actually can shine. So we all think of dark matter being completely dark. Not true. Oh, good, I'm going to finish on time. Not true. In fact, if dark matter is a supersymmetric particle, it turns out that supersymmetric particles are what we call Majorana particles, in which the particle and the antiparticle are the same thing. So if you get, particles and antiparticles in the case of cold dark matter are the same particle, usually nothing happens because the dark matter is very diffuse. But where the dark matter is very centrally concentrated, like in NFW cusps, there the density is so high that there could be annihilation of dark matter and anti-dark matter. And that annihilation would show up through the emission of gamma rays. And so that is what the Fermi satellite is looking for, amongst other things. In principle, the Fermi satellite could see the gamma ray radiation arising from the annihilation of these supersymmetric particles. The intensity of the radiation depends on the square of the halo density because it's a collision, and it depends on particle physics through the cross-section. But now with the simulations that I show you, we know exactly what the density profile is, and we can then make predictions for what the Fermi satellite should see. And it turns out that wherever you see a dense spot, you should see lots of gamma rays with an energy of a few hundred GeV and a characteristic spectrum that particle physicists can predict. You should see these gamma rays coming from the center and from the lumps. Here are the predictions that we made 2 years ago for what the gamma ray sky should look like in annihilation radiation. So the center should be booming through because that's where the maximum density is achieved, and this is a rho squared phenomenon. And then you should, in principle, also be able to see some of the lumps. Of course, most of these lumps don't have any galaxies in them. They don't have any stars in them. So if these ideas are right, then Fermi should see first the center, although it's difficult for reasons I'll tell you about in a minute, but also it should see lumps of concentrated spots of high intensity where there are no stars. And these are these empty little subhalos. And Fermi in principle should see this. Here is the image that Fermi published a few months ago. And you see the galaxy. And unfortunately, this is not the Nobel Prize hiding behind this. This is actually just a radiation emission, foreground emission. And the problem is that in the center where we expect most of the dark matter signal, there is also where we have most astrophysical sources which contaminate the emission and make it hard. However, there is an expectation that perhaps this might be seen in the next few years. So let me summarize then. As I said, ΛCDM provides an excellent description of what we see in our universe at the expense of three big assumptions: quantum fluctuations, dark energy, and dark matter. But the future looks pretty good because Planck, in fact, will tell us perhaps whether inflation really happened by looking for B-mode polarization. Dark energy, I think that's a much tougher problem. I don't think it's very likely that this problem will be solved soon, but in principle, at least the astronomers are trying to contribute by trying to measure the value of W. But I think the progress here is perhaps less imminent than it is in the subject of trying to discover the nature of the dark matter. I've argued today that in the Milky Way, both the satellite photometric and kinematic internal data seem to be consistent with the predicted cusps. This so-called satellite problem is probably explained by galaxy formation, and we're beginning to see through the stellar streams perhaps evidence that the Milky Way formed in one of these great movies that CDM theories make. The future here also looks very good with telescopes like Pan-STARRS that will map the Milky Way halo with greater detail, and of course the ESA mission Gaia, which will fly, in which Spain is a part, and will fly in the next 2 or 3 years. Eventually, as I said, don't believe anything until the dark matter is discovered, and there's everything to play for there. So let me then finish off by telling you that even though I had a lot of fun in the 1980s doing cosmology, that was not the golden era. The golden era is probably just beginning. And I'll stop here.
Thank you, Carlos. Questions? Ignacio?
Carlos, I have 2 questions. The first one is related to the Caspi or core problem. No? So during years, people use low superbrightness galaxies as a test bed for the theory, and they found that the data was most consistent with the idea of cores. So I would like to know what do you think about that?
Low surface brightness galaxies.
With the low super brightness galaxies. And the second question is related to the idea of the reionization for removing the number of satellite galaxies in the Milky Way. No? So do we have any other observational evidence for checking that the reionization could be the one of the mechanisms, or is this just one idea that we use for removing satellites and we cannot find another evidence in another astrophysical context? So,
okay, so let me tell you first about low surface brightness galaxies. Now, when people talk to me about, first of all, let me say one thing. Of the whole sample of low surface brightness galaxies that have been studied, 90% are consistent with NFW profiles. It's only these few that are not, that of course people make a big fuss about. Now, so you have to bear in mind that most LSBs do seem to be consistent with cusps. Now, the cases where they don't, well, when this story began in the 1990s, and with low surface brightness galaxies being always shown to be discrepant, the subject was very confusing because a lot of the observations were really being overinterpreted. So, for example, it turned out that a lot of the H1 maps were suffering from saturation and poor resolution. Then when H-alpha maps were used, it turned out that when you looked at the galaxies, because these measurements come from assuming rotation curves that are produced by equilibrium gas, that the gas was all lumpy and clearly out of equilibrium. So I would dispute a lot of the data. I think the data were overinterpreted. However, there are some good cases where you can really see there's no evidence for problems, instrumental problems with the H1 measurements, and where the H-alpha looks quite smooth. Now, and I think those are real interesting objects, and I wouldn't be surprised if they do have cores. However, I always ask the question, explain to me first, why is this big halo harboring a low surface brightness galaxy? Why is it low surface brightness? People use them because they have relatively small baryons, but something must have caused this galaxy to be low surface brightness, and perhaps whatever caused the low surface brightness also affected the structure of the halo. So my view on this, and I've written a paper on that, which I rank as one of the worst papers I've ever written, with Julio Navarro, arguing that if you could engineer explosions in the centers of cuspy halos, then you could combine the center and produce cores. So I don't put that possibility out of sight. So that's why I like the satellites, because there we understand why they have so few baryons, and brings me to the second part of your question, Ignacio. And the interesting thing is that you don't expect to see any direct evidence of reionization in the satellites that survived. If you look at my simulations with Okamoto, there we have a plot that I didn't show. Well, I showed it, but I didn't discuss it, where you see that galaxies that actually make a satellite, they go through reionization, and all reionization does is it pops out the gas a little bit, but you don't see any consequences. What reionization does is that if a halo is too small, it just photoevaporates the gas, and that is destined to become a dark halo. And so in the satellites that you do see, it's very difficult to see any evidence for reionization. Contrary to what some people think, reionization doesn't eject gas. Supernovae does that. All reionization does is makes little halos. It just makes them barren because the gas doesn't cool. Now, there are indirect things you could try to look for in metallicity patterns, for example, and things like that, but that would not just be a test of reionization, but of the whole picture with supernovae and so on. So I hope that answered your two questions. Very good questions. Thank you for those.
Okay. Pablo?
So you have concentrated your talk on comparing the models with the nearby universe, and you have shown that current models do a very nice job in reproducing the stellar mass function and the larger scale structure. But observationally, we are seeing more and more evidence that very, very massive galaxies were in place very early in the lifetime of the universe. Observers like to call this downsizing, and sometimes I get the impression that modelers don't like that word because you didn't mention. So what are your thoughts on that? Do you think that it's still a problem for models to this downsizing scenario? And do you think the problem is related to how we put the baryons on the models, or it could be related to the cold dark matter web?
Yeah, a good question too. So I think so what we have to bear in mind, right, when we talk about downsizing, first of all, it's one of those words that if you ask, I know who invented it, Len Cowie invented it. And I've asked Len Cowie and Günther Hasinger, who wrote all the big downsizing paper, what do you mean by downsizing? And they all give you different explanations. But in effect, at first sight, downsizing means that big things were doing their thing, be they quasars or galaxies at high redshift, and today is the day of the dwarf. So dwarfs are doing their things today. Big galaxies seem to have done them at high redshift. Quasars were bright at redshift 2. They are not bright today. If you look at where are the stars forming in our surroundings, they're being formed in the LMC, which is a dwarf, not in the big things. That's roughly what downsizing means. And at first sight, It's exactly the opposite of what cold dark matter predicts, because in cold dark matter, as we saw in the movie, small structures form first and big structures form later on. And so at first sight, what we see in nature, it seems to be, and I've written a paper called anti-hierarchical. Now, however, what we have to bear in mind is the second part of your question, namely, what grows hierarchically in CDM is the dark matter. The baryon processes don't need to follow, and we've seen an example with the satellites, the evolution of the dark matter at all, because baryonic processes are subject to gas dynamics, to energetic effects that affect even the content of halos and so on. And so one has to bear in mind that what we observe when we look at downsizing at baryonic processes, and just to give you an example, if you have lots of fuel, lots of gas in a galaxy, on a quasar, for example, but you use it all up by redshift 2 and you have no more because you ran out of it or you blew it out, then naturally you wouldn't expect your successors to be as bright. And so I think this downsizing is something that can in principle be understood by putting in all the baryonic physics into the theory. And so there are many examples, in fact, of such efforts. There's work from Bauer et al. In Durham, Croton et al. In the MPA, and many other people after that, the Italian group that does similarly. So I think we're now not surprised by this downsizing. But at first, I would agree with you that the first reaction one should have is what's going on here? There's something weird. And I think what's weird is just baryonic physics are strange and don't track the evolution of the dark matter closely. And I think the satellites are a very nice example of that, right? That how baryonic and dark matter physics get decoupled at early times. So in summary, I don't think downsizing really is a fatal problem. I think it's a fascinating aspect of galaxy formation, and it's telling us that our understanding of galaxy formation is still quite crude. But I think we couldn't really rule out cosmology any more than in the 1970s and 1980s people could rule out cosmological ideas on the basis, for example, of the number counts of radio sources. And you remember, but you're not old enough, but neither am I, but in those days, people would say, well, we can tell what omega is and so on just by counting radio galaxies, until somebody pointed out that radio galaxies actually evolved. So I think it's the same kind of situation now. Interesting, fascinating subject, but I don't think it'll tell us much about cold dark matter.
Okay, I think we'll stop now. So let's thank Carlos and all the speakers of the morning again.